Hi everyone, today we're going to be looking at the internal energy of a system, what it means. We're going to look at what happens to the internal energy at absolute zero, and how increases in the internal energy affect temperature, also any changes in the internal energy during a phase change. So we're going to have a look at that first, and then at the thermal properties of materials, which links to the specific capacity, and experimental work that can be done to determine that. The first part that we're going to look at is the internal energy of a system, and we're going to see it as the sum of the random distribution. This is a very important part. It's the sum of the random distribution of kinetic and potential energies associated within the molecules of a system. I'm just going to quickly define what we mean by a system. In thermal physics, a system is simply a large number of particles. Like that could be atoms, molecules, or even ions. Now, since we consider a system to be a large number of particles, so for example, like all the molecules in a gas that's in a container. And then we're going to also describe how energy gets transferred between that system and the surroundings of that system. So it could be that I have a container with a lot of gas particles or molecules. That's my system, and then how it interacts with the surroundings. So for example, if it was connected to another container, or in general to the normal air around it. Thermodynamics does look into the properties of a system that are independent of its position and motion, but we have to look at the internal energy of that system. So the internal energy of a glass of water. Now in the glass of water we have water molecules, loads of them. And if it's at room temperature, then the kinetic energy of these particles will be lower than the cap, that's so let's say 20 degrees Celsius. The kinetic energy of those particles in this system, this cup of water, will be lower for 20 degrees than for 100 degrees. And that's due to obviously the particles having less energy and moving slower compared to the ones that are moving faster in the 100 degrees Celsius cup. So kinetic energy is usually based on the movement of the particles. So they have the bigger mass, so we know kinetic energy is equal to a half mv squared. Depending on what we have in there, if their mass is bigger and their speed is higher, then the kinetic energy will be higher in terms of internal energy. So what we are considering is these individual particles' kinetic energies, so hence why we define the internal energy as the sum, so basically the total of the randomly distributed kinetic energies. Randomly means that obviously all particles move at different speeds and they're not all the same. So that's why we have to clearly define that in our definitions when we define internal energy. And when we talk about potential energy, it actually refers to the energy due to electrostatic intermolecular forces between the molecules. So while molecules are quite close together, like in a solid or in a liquid, they have higher potential energies. They actually are so close to each other that they store more energy due to those attractive forces. So that's what we mean by potential energy. This leads to this connects quite closely to the fact that you have positive nucleuses and the electrons surrounding them. Then you might think, but shouldn't they repel if the electron clouds are there? There is actually a point where it becomes repulsive if they're too close. So the nuclei are repulsive when they get too close, but after a certain point between the nuclei, after a specific distance, it becomes very attractive, the force between them, and we'll have more look at that when we go through nuclear physics. But the idea is that they do have intermolecular forces holding them into a very good arranged, regular arrangement in a solid, or into being too close near each other in a liquid. But when you come to gases, the potential energy is very little compared to the others because of how far they are from each other. So there's not a high attractive force between them. It will get a little bit complicated near the end of the chapter, but I will explain that as we go. So yeah, the total energy takes into account, if I was to write in simple terms, and by the way, you can't use this as a definition though, is internal energy is usually represented by U, but you don't have to know that for this course, is equal to kinetic energies plus potential energies within the system. So basically, it solely relies on how the molecules are moving and how they're arranged within the system in terms of the potential energy. Okay, so what happens when I cool a substance or in a system, or water, anything that it could be? The molecule movement will slow down. And obviously, since you have slower moving molecules or particles or atoms, then your kinetic energy of the system gets less. And since the internal energy, we said, is the kinetic energy plus the potential energy, that means that since your kinetic energy dropped, so will your internal energy of the system. If I start heating a substance, the molecules will move faster, which means the kinetic energy increases, which means the internal energy increases. Now, what will happen at absolute zero? This is something very, very important. What happens at absolute zero? Then, at absolute zero is the lowest temperature possible. That's when particles will, or molecules, whatever you want to pick, will stop moving. So particles stop moving completely at absolute zero. Remember, absolute zero stands for 0 Kelvin. That's the lowest possible temperature ever. They have managed to get that in lab. Well, not absolute zero. We can't get to absolute zero at all. But they have managed to get up to 1 times 10 to the minus 10 Kelvin in the lab. And also in deep space, the temperature between galaxies is actually about 2.7 Kelvin, so it's really, really cold. And remember that 0 Kelvin is minus 273 degrees Celsius. So it is quite cold. If it's 2.7 Kelvin between galaxies, then that means it's minus 270 degrees. So it's quite a very, very cold temperature. But they did manage to get quite close to zero, absolute zero, but not to absolute zero in labs yet. We said already that particles stop moving. So if they stop moving, that means there is no, since kinetic energy is a half mv squared, there is no speed, no movement. So if we multiply numbers by 0, then the kinetic energy tends to be 0 joules. That means that the internal energy solely depends on the energy due to the attractive forces between the particles. Now, obviously, you can't get rid of the attractive force between those particles, so at absolute zero, the internal energy is not 0. It instead relies on the some of the random distributions of the potential energy only. That's a very important part, and it's part of the course that you have to know. So you can see here, one of the specification points said the absolute zero as the lowest limit of temperature. For temperature, there's nothing lower than that. And that's the temperature at which a substance will have the minimum internal energy, meaning that it will only rely on the potential energy. You should be able to state this in questions. We're going to talk about how there's an increase in the internal energy of a body as the temperature rises, and the changes in internal energy during a phase change, constant temperature during a phase change as well. That's the next part I'm going to talk about. Okay, so what happens when we increase the temperature of a body? I already mentioned, of a substance, I already said that any temperature changes will affect the kinetic energy of a system. And so if I increase the temperature, then the kinetic energy increases. So the hotter a substance is, the more kinetic energy the particles individually will have, the faster they will move, but at random speeds faster, obviously, because they collide and everything with each other. And the higher the kinetic energy will be. So I know that I can increase the internal energy if I increase the temperature. As the kinetic energy will increase. Remember U, so internal energy is kinetic energy plus potential energy. So I can just simply increase the internal energy of a system, so the thermal energy stored within a system, by increasing the kinetic energy of the particles within that system, just by increasing the temperature. And there's a graph here that shows just simply heating up a substance as time goes by. So this is a time axis. This is a temperature axis. Maybe you can't see that clearly. And you can see as time goes by, while I'm increasing the temperature, heating up a substance, it starts off as a solid here. And as time goes by, the temperature, so these are time points, time increments. As time increases, the solid reaches a point where its temperature stops increasing. Now this is when we have a phase change. So when you have solid changing into liquid for a specific amount of time, the temperature remains constant. So at this point here, you can see that it's a flat line. The temperature stays constant. That's the melting point. And what happens there? So if I can't increase the temperature anymore at this point, because of the change phase that's taking place, the phase changes that are taking place at that point, then obviously something else is happening, because the internal energy is still increasing, but we can't see a temperature change. That's where the special magic happens. So basically you don't have a temperature increase, so no kinetic energy change, there's no kinetic energy increase at all, but there is potential energy increase. That has to do with potential energy between the bonds increasing. So when there is a phase change, we can increase internal energy if phase change by potential energy increasing. So now what you have is constant kinetic energy, but an increase in the potential energy. So the internal energy is constantly increasing, but when there's a phase change, that's when the the internal energy always increases, but when you have a phase change, the potential energy increases, whereas the kinetic energy stops increasing. And obviously, after that point, after this point here, once the substance has fully changed phase, so it went from a solid to a liquid, the temperature starts rising again until this point here, when you have a liquid changing into a gas. So we have this long, in this diagram, we have this long phase change. Obviously you can see here that that's the boiling point as well. And that's when you have the liquid changing into gas. So once again, you have only increases in the potential energy of the system. So let's move on to the next part. So before actually I move on, just a little summary. To increase the internal energy of a body, you need to either increase the temperature, which will increase the kinetic energy, or to put it through a change of phase, which increases the potential energy. Also, very quick point to mention here is that when there is a phase change, no temperature changes. It will remain constant. And that's very important because you have to always mention it in your answers. Okay, here it will get a little bit confusing because I'm going to talk about the electrostatic potential energies in terms of how they appear in gas, liquids, and solids. We already said that since gas particles are too far apart, they don't tend to have strong attractive forces. So they have the weakest attractive forces between them. That means that there is such a negligible potential energy between them, holding them together, that we say that the potential energy of a gas is 0 joules. Now if we go to a liquid, since they're closer together, they experience stronger electrostatic forces than gases, and hence they do have potential energy. However, the value will be a negative value. So I'm going to just use an example here, by the way. This is not a realistic value. It's just for you to imagine it. So let's say minus 100 joules. The reason we say minus, we give potential energy to be negative, is because we need to provide that energy to break those bonds. So by heating, that's thermal energy. We're providing it with thermal energy that will be enough to overcome the electrostatic attractive forces between the atoms, molecules, or ions in that substance. Then we have solids, which are very close to each other. I know my diagrams are not the best, but it's just an idea. You already know these diagrams. They're much closer together. They're held much strongly together in a regular pattern. Hence, it will have a very large negative value because there's a lot of stored potential energy between them. Obviously, once those bonds are broken, the energy is released. But while the solid is still in a solid form, it has very large stores of potential energy. However, since we need to provide the energy, it is much higher than the liquids and the gas. However, when we talk about which actual one has the highest potential energy, due to them being negative, so due to this number being negative and this being negative, the highest potential energy is possessed by the gas, then the liquid, then the solid. And it also makes sense because we saw in the diagram of the temperature increasing with time. If I'm heating a substance, by the way, this is a heating curve, not a cooling curve. So if I'm heating a substance up, then you can see that we said that the internal energy of the system increases, and we're going from solid to gas. So gas does have the highest potential energy, and we did say that the internal energy increases at phase changes due to the potential energy increasing. It is a little bit confusing, this part, but if you do have questions, please ask me in the lesson. Okay, so now we're going to look at specific heat capacity. The specific heat capacity is defined as the energy required per unit mass to change the temperature by 1 Kelvin. It's quite simple, actually. It's how much energy do we need to provide let's say, water to increase the temperature by 1 degree Celsius for 1 kilogram of water, for example. We have the equation here. These are the symbols. C stands for the specific heat capacity. So C is equal to E over m delta theta. You have this equation given to you in the formula booklet as in this format. But yeah, the m stands for the mass of the body. So you're not always going to be looking at increasing the temperature of 1 kilogram only, but this is for simplicity. So how much energy do I need to provide to 1 kilogram of water to increase its temperature by 1 degree Celsius or 1 Kelvin? Remember, temperature change is the same for both. So if I wanted, for example, to say was the temperature change between 100 degrees Celsius and 0 degrees Celsius, the temperature change is 100 degrees Celsius. If I have it in Kelvin, 0 degrees Celsius is actually 273 Kelvin, and 100 degrees Celsius is 373 Kelvin. So what's the change in that is 100 Kelvin. When we use temperature on its own, not as a temperature change, we will need to use Kelvin only. So you don't have to convert if you gain the temperature change, because it simply gives you the same amount of change between temperatures. We said M stands for the mass of the body, always given in kilograms, always put in the equation as kilograms. Specific heat capacity is joules per kilogram per Kelvin, and you can figure that out from the equation because you have the units of energy, which are joules, and then that's divided by kilograms mass and Kelvin for the temperature. So joules, kg minus 1, k minus 1. Delta always stands for, so this symbol here, delta, stands for the change, and theta stands for the temperature, so change in temperature. And E always stands for energy. In this case will be thermal energy that will be either supplied to a body or lost by the body. So if you have a temperature going down, decreasing, then that's the energy that will be lost by the body. If the temperature is increasing, that's the energy that will be supplied to the body and gained by the body. Now, I spoke about water being special in terms of its density at solid and liquid state, but water is also very special in terms of having a very high specific heat capacity. Now that means that if you want to increase the temperature of water by 1 Kelvin, so 1 kilogram of water by 1 Kelvin, then you have to supply 4,200 joules for it to increase just by 1 Kelvin or 1 degree Celsius, if you want to think of it in that way. Metals usually have low specific heat capacities. For example, lead. Lead has a specific heat capacity of 129 joules per kilogram per Kelvin. That means that you will need to provide 129 joules of energy to increase 1 kilogram mass of lead by 1 degree Celsius or 1 Kelvin. So that's basically talking in terms of, okay, which object will get hotter with, so much amount of energy in such amount of time. So a lot of substances have their own specific capacity. They all have their own unique specific capacity, and they do consider these parts in terms of how they use them when they build electrical components or anything. So for example, car engines use water as a coolant because it takes a lot of energy to increase the temperature of water. They also use water in nuclear reactors because it requires a high amount of energy to increase the temperature of water and so on. And also, once water reaches a high temperature, it's also harder for it to lose it. That's why we use it in our home heaters, the ones that are connected to the wall, the ones that are not electrical. So water retains its temperature for quite a while. That's why when you turn the heating off, it's still warm long after that, because you have a pipe of water behind it going through the heater. Now, obviously, a good point to make here is that this calculation can only be done when the object is increasing in temperature. If it is at a phase change, so for example, going from a solid to a liquid, this equation doesn't apply. We'll be having a look in the next lesson about that. Okay, so let's say I have 1 kilogram of copper and 1 kilogram of aluminium. They both have different specific heat capacities. So copper has 385 joules per kilogram per Kelvin, and aluminium has 900 joules per kilogram per Kelvin. Let's say I want to increase both of these metal blocks' temperature by 40 Kelvin, let's say. So I want my change in temperature to be 40 Kelvin. Let's say they were, at 10 degrees Celsius and 50 degrees Celsius. And I want them to get to 50 degrees Celsius, sorry. Then if I calculate the energy for each one of them, it will be 1 kilogram times 385 times 40. That leaves you with about 15,400 joules. And the same thing for the same mass of the block, but to be increased by the same amount of temperature. So the only thing that they rely on both is the specific heat capacity. So that's going to be 1 times 900 times 40, which gives us 36,000 joules. So you can see that the aluminium block requires much more energy to increase its temperature by 40 Kelvin compared to the copper block, which has a lower specific heat capacity, which requires less amount of energy to increase its temperature. You see, this is how to investigate specific capacity of a specific solid that we could be given. What you have is an electric heater here. So this is an electric heater. So we're providing energy to that heater through a circuit. We have we know how to measure the energy provided, because we know that energy is power times time. We know that power is voltage or potential difference times current times time for the whole energy to be calculated, since power is energy over time, and since power is also IV. So what we have, can measure the energy that we provide to the system through the electric heater using this equation. And we can take our readings, obviously, using an ammeter, a voltmeter, and for time you can use a stopwatch. And then you leave it on, so you start the timer, you start the heater, you leave it on, and then you can measure the original starting temperature and final temperature using a thermometer. Usually in exams, you don't have to fully describe it. You can label a clear diagram and show exactly what you're going to be using to measure what, and what calculations you will have to make as well. This is the metal block that's getting heated. And you also need insulation around the metal block, so you avoid any thermal energy being transferred from the solid to the surroundings. So what you have is your electric heater heating up the metal But thermal energy doesn't always remain where you want it to remain, because it always goes from hotter to colder. So obviously the surroundings are colder. So we're going to try and avoid the thermal energy escaping, because if the thermal energy escapes, the temperature of the object will be lower at each point than when it should have been higher. And then you will need to provide more energy to the system in order to keep the temperature where you need it to reach, the final temperature. So usually that's one of the biggest experimental problems we have with this setup, is that you need good insulation. Even with insulation, it doesn't necessarily mean that you don't lose any energy. It just means that you lose less than originally. So as I already said, you can calculate the energy transfer using this, but you also need a scale to measure the mass of the block. Since we need I, we already said how to measure that, V, how to measure that, time, how to measure that. A change in temperature can be measured with thermometer. And then you just need a scale to measure the mass as well. So once you have all these values experimentally, you can determine the specific heat capacity. But doing this experiment once only and leaving it like that will not give you accurate results. To be able to get accurate results, you need to plot a graph of temperature of the substance against time. So you will need to have, while you're recording the temperature, you should record it at, instead of having a starting and final temperature, you should be recording it at different intervals, time intervals. So for example, every minute. So you should take the reading of the temperature and create a graph. Obviously, you still have starting and final temperature, but this makes your results more accurate because you have a range of measurements to take, and you can spot the anomalies and all of this analysis that you need to do. Now, how is that going to even help us in terms of, the graph that we get and the gradient that we get? So you'll get a straight line, hopefully, passing through part of the y-axis, because obviously at time 0, the block is not going to be in ice. It's not going to start at 0, so it will probably start at room temperature or something, about 20 degrees maybe, and so on. But this leaves us with a gradient of change in temperature divided by change in time. Now, how does that fit into your analysis of the calculations? I'll show you now. So we have this equation that we will need to analyze using the gradient. Now, if I divide both sides by delta T, because whatever I do to one side, I have to do to the other side. Oh, sorry, delta T. You end up having this expression that you have as a gradient. And on this side, you have E divided by change in time. So basically what you'll be under your x-axis. We know that E divided by T, if you look back here, it's power. So in other words, if I simplify my equation, power is equal to mc delta theta over delta T. And we already said that power is equal to I times V. So what you will end up with is, or you can leave it as power. If you want to get the value of specific heat capacity, you just rearrange this equation. It will be power, this is a gradient, remember, so this is the gradient that you're going to get. It's going to be specific heat capacity is power divided by m times gradient. You can also do this experiment for a liquid. So instead of, you will still have a heater. You also have a shield around it so that you can insulate it. But you will also need, the only difference that you will need is for liquid, to determine the specific heat capacity of a liquid, you will need a stirrer. And that's to ensure that you have even temperature around the liquid at all times, because as you know, you have convection current, so you have hot water rising and cold water taking its place. So you need to make sure that it's very well mixed each time that you take the measurements. In class, I will also introduce another method called the method of mixtures. That will help you make calculations of specific heat capacity if you know the masses of the two substances at different temperatures when they're mixed together. But I will have to go through that in class when we look through questions. So this is something that we'll be looking in class. Okay, so going back to the learning objectives, we have seen all of the first points we made. We talked about the specific capacity, an experiment to measure the specific capacity of a metal or a liquid, and the techniques used to determine the specific capacity of a metal block and a liquid. Okay, so far we have looked at all of these points. Here, we've done them. We talked about the specific capacity, how to perform an experiment, and techniques and procedures to analyze. The only thing left is to look at the method of mixtures to make an estimation of specific capacity, which is mostly a mathematical view and a little bit of the method.